If an object is acted on by a constant force of magnitude F, and the object moves in a straight line over a distance x, then the work done, W, by the force F is the product of the component of the force in the direction of motion and x. So let's look at this example here. We have this object positioned at 0, and sometime later it's at this position over here. Now it follows a straight line path. Now that's important. That's a simplification that we are going to use in this course, that the object is moving in a straight line path. So it moves from here to here over a distance of 20 meters. We have a force of magnitude 100 newtons pointing horizontally, that is in the direction of motion. To get the work done by this force, we take the component of this force in the direction of motion. Now the component of this force in the direction of motion is just the force itself, actually, because the force has no vertical component. Okay, so the magnitude of the component of the force in the direction of motion is 100, and we multiply that by the distance, the straight line distance that the object moves, which is 20. So this force is constantly acting on the object while the object goes from here to here. So the work done is written Newton meters, and the Newton meter is called a joule. Okay, so I just multiply the two units here to get a Newton meter, and that's called a joule. Now it's important to realize that this force might not be the only force acting on the object. Of course, if the object is near the surface of the Earth, we have the force of gravity acting on the object. Because the object is in contact with some horizontal surface, we have a contact force acting on the object due to this surface. There may be many other forces acting on it. And as for the resultant force could be pointing in any direction. But what we do know is that the object follows a straight line path from here to here, even if the resultant force is not along that direction. It's quite possible that the resultant force could be pointing to the left. It's quite possible that the object could be actually slowing down because there's a resultant force acting to the left. Now we could consider the work done by any of the forces acting on it, but we're only looking at this particular force, which I'm calling F. Now let's do another example. Let's consider a different constant force acting on this object. This force has the same magnitude as the force we just saw, 100 newtons, but this time it acts at an angle of 60 degrees to the direction of motion. So the direction of motion is this way. So again, the object starts here, moves in a straight line path, and ends up over here. It doesn't move in an upwards direction or to the left. It just moves to the right, purely in the horizontal direction. So again, many other forces may be acting on this. Okay, what do? Well, we get the component of this force in the direction of motion. So we just project the tip of the vector down onto the horizontal, because the direction of motion is in the horizontal direction. We multiply the magnitude of this vector, which is 100, by the cos of 60 to get the magnitude of that component. Now since the cos of 60 is a half, the magnitude of this component is 50. So the work done by F, which I'm calling W, is the magnitude of the component in the direction of motion, 50 newtons, times the distance through which the object travels, is 20 meters. So we get 1000 Newton meters. Notice that the mass of this object doesn't come into any of this. We are only dealing with the work done by this force. The work done by this force will be the same regardless of what mass this object has. So we get an answer of 1000 joules. Now, let's suppose that we want the work done by this particular force. Now this force is perpendicular to the direction of motion of the object. So I'll call the work done by this particular force W. We need the component of F in the direction of motion. Now you can see that if we project the tip of this vector onto the horizontal, we get a component of 0 length. So the magnitude of the component of this force in the direction of motion is 0, and the object moves a distance of 20 meters in a straight line. So we get 0 Newton meters. which is 0 joules. So as long as the force is perpendicular to the direction of motion of an object, the work done by that force is 0. Now we will see this idea later when we consider the motion of a pendulum bob, and the work done by the string tension on the pendulum bob. Okay, so we'll see more about that later. I won't go into it now. Let's get the work done on the object by this particular force. Now again, the object starts here, moves in a straight line path and ends up at x equals 20. Now we want a component of the force in the direction of motion. Okay, so if we project the tip of this vector down onto the horizontal, we will see now that the component is pointing in a direction that's opposite to the direction of motion. So we could multiply 100 by cos 60 to get the magnitude of this vector. Now, we did a problem very similar to this a few minutes ago, but vector f was in this direction. So what's the difference in this situation? Well, the magnitude of the component will be the same, but if we follow the formal definition of the component of a vector, we would be measuring the angle anti-clockwise from the positive x-axis. So we are assuming that the object is moving in the direction of the positive x-axis, and this angle here is 120 degrees. So when we're getting this component, well, we are not talking about the magnitude of it now, but we're thinking of it as a vector. We would have to multiply the magnitude of the vector, which is 100, by the cos of not 60 degrees but 120 degrees, and then we multiply by 20 meters. But you see, the cos of 120 degrees is actually minus a half, so we'll actually get minus 50 newtons, whereas in the earlier example we got plus 50 newtons. So you see, the component of f in the direction of motion is negative. Okay, it's pointing to the left, and we were assuming all along actually that vectors pointing to the right were positive vectors. Now this negative sign is important because obviously this situation here, the work done by this force, is hardly the same as the work done by this force here, which also has a magnitude of 100 and makes an angle of 60 degrees with the horizontal. So for this particular force, we say that it does negative work. As a matter of fact, we can say that the work done by the object, not by the force, but by the object, is plus 1000 joules. So if the work done by a force on an object is negative, then the work done by the object in opposing that particular force, if you like, is plus 1000 joules. But we won't worry too much about that for now. So we always get a negative value for the work done by a force if the component of that force is in a direction that's opposite the direction of motion. Now let's consider the work done by the force of gravity on a bag of sugar as it falls through a distance of 1 meter. So it falls vertically down to the floor. Well, the force of gravity on the bag of sugar, or the weight of the bag of sugar, is entirely in the direction of motion of the bag of sugar if we leave the bag of sugar fall vertically down. We know from Newton's second law that the force of gravity on an object near the Earth's surface is the mass times the acceleration due to gravity. All objects have an acceleration of 9.81. G equals 9.81, provided that they are near the surface of the Earth, if we ignore air resistance. But even if we include air resistance, it won't matter here, because we are only interested in the work done by the force of gravity, which is 1g in this case, because m is 1. So we multiply the component of the force that's in the direction of the straight line motion, well, that's just the weight itself, 1g, by the distance that the bag of sugar falls, and we are letting it fall through a distance of 1 meter here. So we get 9.81 Newton meters, which is 9.81 joules. So that's the work by gravity done on the bag of sugar, and we can actually say that the energy of this bag of sugar is 9.81 joules. Not the energy of it if it is eaten, of course, but the energy of it due to its position over the surface of the Earth.